Hello, I'm at the University of Sussex with Paul Graham and Thomas Nortney. Happy to be here and be able to talk a bit about ant navigation. So, as you can guess by the title, I use spiking neural networks to investigate it. And the reason why is because of the biological plausibility. I like to use a system that you can look at the membrane potentials of the system, and it feels a lot closer to the actual biology, which is why I use spiking neural networks. There are also, when you get to the robotic side of things, there are also efficiency gains. They are a lot more efficient than artificial neural networks because of the nature of having systems that are on and off rather than continual activation of multiple values. And also embodying these systems and robots can really help us to um, embody our theories essentially and test our theories online on a robot in the real world. So I work on route following. So I focus on just the route following behavior, which is mediated by the mushroom body region here. And that's what I model. It's well known, as many of the people here would know, well known for that its importance in route following. It's an important experiment with these lesion experiments where they train the ant to go in a certain direction to home. And essentially, once you lesion the mushroom body, they can no longer navigate in that direction effectively. So we know that the mushroom body is really important in this area. So just to take you through the computation and an outline of my model. So if we put an image into the model, it goes into the first the visual projection neurons, which in my model there's 320, depending on the resolution. And then it gets into a much higher space of the Kenyan cells, with 20,000 Kenyan cells being there. And then the mushroom body output neuron. Now, if you put this input image in, you get this specific arrangement of activations going through the network. Um, and then that activates the mushroom body. Now, since there's an anti-Hebbian learning rule, it means that these connections will weaken because if they're spiked in close in time, the connection weakens because it's anti-Hebbian. So that if you put the same image in, you get the same activation going throughout the network, and then it won't spike, showing that something is familiar. So this is what the model shows when it's learned something. So with this model, so in terms of these projection neurons as the input, they essentially take very low resolution images. Well, low resolution as ants have much lower resolution eyes than ours. And we also have some normalizing inhibition on the Kenyan cells as well. So in terms of how we convert the mushroom body activity into heading directions, we do it similar to the RIDFs that you saw in Stathis talk, where we get this activity throughout the network, through the Kenyan and the M-bonds, and essentially our familiarity rating is the amount of M-bond activity. We've only got a single M-bond here to keep it simple, but at every point in a route, we can essentially scan through, show it the image, and then cycle through rotations of that image multiple times until we find what is the minimum, and it will go in that direction. So we wanted to do this on a larger data set to see what would find in terms of what are the important characteristics of the network, what affects the memory capacity and things like that. So we have the Stanmer outdoor data set, which you've seen a little bit already, this robot going around, and have that in a panoramic image, which we can feed into the network with lots of different parameters. Now, in our parameter search, this is actually just a tiny subset of it, but there's still a lot of results in here. But the key thing that we found is that um, the performance and memory capacity of the model just depends on how much stimulation reaches the Kenyan cells. And there's a delicate balance between how much it can receive and um, how much it can remember. So, for example, if you increase the presentation time, that allows more information to get through to the Kenyan cells. If you increase the amount of connections from the VPNs to the Kenyan cells, that also can like rapidly increase the amount of information that gets through. And if you get too much going through, then too many Kenyan cells fire, meaning that too many synapses between the cases and M-bonds weaken, so too much is familiar. That produced one interesting effect of, let's say you train the model on from a large route, you train it on just small increments of the route. So let's say you have 200 images and you train it on only 20 of those spaced out evenly throughout the route. That means that even if it's learnt a small parts of the route, it can have much higher performance than it would have if you trained it on more of the route, which was quite different to lots of our more standard visual navigation um, models. So we found the best performing area, which was here, and then we use those parameters for our real world tests, essentially. So in our real world performance, so we have this indoor environment in the lab in Sussex, and this allows us to test a lot of routes. So here's a couple examples of routes. The black line here is actually the training route. So that's where we train the model going through the first time. And then the colored lines are the different models. So we tested perfect memory, which is essentially just a database. It's just an image database. It remembers everything it's seen before. So when it comes up with something in front of it, it just does a pixel-wise comparison with everything it's seen before. And then Infomax is a small single layer neural network that's used a lot in other visual navigation experiments. And then the mushroom body is our spiking model that we tested. So this is a video of it working. This is sped up 10 times though, because it's quite slow at the moment because of testing all the rotations possible of each image, which can take quite a long time. But still, in terms of navigation performance, we found it very, very comparable to the other standard visual navigation algorithms. And when showing some of the comparisons, it even showed more consistent results as its deviation was a lot less. Well, its range of deviation was a lot less than the other models. So it's quite robust. And this is just from a simple, it's got one simple learning rule, and it keeps track of everything it's learned before. When it's doing this comparison, it's just comparing what it's seeing now to everything it's ever seen before, essentially, because it's not specifically saying, do you remember the closest image? It's just taking it from all the information that it's learned. So going into what I'm focusing on now and my overall PhD. So that's kind of one step, which was getting a spiking neural network working of an ant brain region. But I'd like to have this loop, kind of like with Blaze, what he was saying, of having this models connected to the behavior, connected to the environment through a simulation. And the one tool that I found that has been really useful so far and hoping to develop a lot more into is NVIDIA Omniverse and Isaacson. So speaking of file formats, so they use the OpenUSD file format for everything. And this is a open file format developed by Pixar, where it can be human readable and allows you to interact with lots and lots of different applications. So from the apps that you use to scan in your 3D model, whether it's using LiDAR or other techniques, to the simulation itself, to the image modification. You can do all of this within one file type. So it's really easy to transfer um, between programs. And also they have a lot of um, virtual robotic support. So you can have your models of the environment connected to your network models that you're wanting to use in embodied simulations, which is why I ended up going for it. As I started with try to see what was going on in Unity, as that's a much more common game engine, which this can connect to. But I found that this had um, through something called Isaac Sim and Isaac Gym, it had things that are ready-made for importing and embodying your networks into a simulation, which would be useful for me as I would like to compare my um, the behavior of ants to the behavior of my model. So we have an ant lab at Sussex, which many of you may have visited. This is a configuration of it that we use for some behavioral experiments. And we take video recordings and track. This is the first track with Deep Lab Cut. Of course, it's got a few errors here and there, which we can filter out with some more training. But this is the kind of trajectory data that we get within this kind of environment. And what the aim of this would be to get these trajectories into Omniverse so that we can have the one-to-one view of what our ants saw during all of these experiments. So we took some LiDAR scans of it. So we tested a few things. There's some mobile apps nowadays so that can do photogrammetry. So where you just take a lot of pictures and then it's processed in the cloud. Um, and then you get the model given back to you. For this, the best scan we got out of was 3D scanner app on iPhone, which the new iPhones having LiDAR, which helped give us a lot more quality in our scans. Of course, there is some errors here, like emission errors, but with some fine tuning on the model in software such as Blender or other open source 3D modeling software, that can be sorted. So just to take you through an example of this. So here we have, I hope it's showing up in the stream okay. But here, for example, we have the Ant Behavioral Lab and we have a virtual robot. And I've scaled this virtual robot to about the size of an ant. And then you've got the scene view here and the first person view of the robot here. And we have some visual scripting here that I'm using to create a controller that can control the robot and then set up cameras to the robot so that we can easily see what's happening with it. And this is a video of the same environment, but just showing some of the programming of the views that it's fairly easy to set up cameras and be able to move them and animate them throughout the environment so that you can have lots of views of your scene. It's also possible to through a system of synthetic data generation, able to extract images from these camera routines so that you can get a lot of images from randomly assorted in the environment or from a specific path to give you lots of options for when training models. And then there are also some different camera models, such as a fisheye lens that we use a lot, that we use quite a bit to get our panoramas. But yeah, so that's where I am right now with the Omniverse. I'd like to right now I'm working on getting my spiking model from the previous investigation more linked up into this so that it can actually drive the robot itself through a custom controller. So the main conclusions from that would be that a biologically inspired model of the atmosphere body can navigate effectively just using a simple learning rule. It doesn't even include much. It's not too complicated, but it can still navigate just following these simple rules. And that its sensitivity to parameter changes is very variable on the amount of data that comes into the Kenyan cells. And also, it seems that Omniverse is really promising for some embodied modeling in the future. And yeah, I'll be very interested to hear how it could be combined with some experiments people are doing that, whether they'll be able to produce scans and incorporate some of the simulation into their work. But yeah, thanks very much for your time.